Alright, welcome everybody. So today we're going to talk about using balanced equations to calculate amounts of quantities that are either reacted or produced. So the way that we do this is we always use something called a mole ratio in a balanced equation. And so the mole ratio, understanding what it is and how it works, is really key to this next and pretty much last part of the chapter. And so when I look at a balanced equation, let's say that I were to have some nitrogen reacting with hydrogen forming ammonia. When I look at this reaction, the mole ratio is built in. The mole ratio is represented by the coefficients. And so what this looks like is as follows. Right here I have 1, even though it's not written, nitrogen and 3 hydrogens producing 2 ammonias. So if somebody asked you what's the mole ratio for this, it is the ratio of the coefficients. It is 1 nitrogen to 3 hydrogens to 2 ammonias. Now this is really important because if I change the moles of one substance, then I will automatically get moles of another substance to be changed in the same ratio. Like let's say, for example, I decide to up the amount of N2 to 2 moles of N2. That's double. That means that I will require 6 H2s and I will require 4 NH3s. So if I put the tags underneath this, N2, H2, NH3, you can see that the ratio can always be reduced back to that lowest whole number ratio between them. And that's an easy increase there, but what if I were to go further? And what if I were to say, well, what if I had, for example, 0.5 moles of N2? Well, now I've cut the amount of N2 in half. And so the amount of H2 will get cut in half to 1.5, and the amount of NH3 will get cut in half to 1. And I could change these numbers any way I want, whether they're pretty or not. All of these are kind of, pretty straightforward. But I could take this in a word format and do something as follows. If I just quickly insert a page here. And so I could do something like this with the same exact equation. It would look like a word problem. It would say, how many moles of NH3 are produced when 0.625 moles of H2 are consumed. Now, people like to do this with ratios, and they can do it with ratios, but I find that using factor label works better. I take the quantity that I have. Let me just take this equation here and copy and paste it so that we can see it down below. Copy, paste. So what I do is I look in my equation and highlight what it is that I'm comparing. And I'm starting with H2 here, and they're being asked how many moles of NH3 can be produced. So that's my mole ratio, 3 to 2. Well, when I look at this, I can do it 2 ways, and I like to do the factor label way. I have 0.625 moles of H2. I can use factor label. The mole ratio becomes the factor, the conversion factor. It's built into the equation. The 2 NH3 being produced uses 3 H2. The H2s will cancel out. And then I will have 6.25 or 0.625 times 2 divided by 3. If I do that in my calculator and I look at that, I get my 0.625 times 2 divided by 3. And I will get 0.417 moles of NH3. Now look, my mole ratio was and is 2 to 3. So I have 2 NH3s in ratio with 3 H2s. Even though in the problem I have 0.625, the amount of NH3 becomes 0.417. Look, if you take 2 divided by 3, you'll get 2/3, or 0.67. If you take 0.417 and divide it by 0.625, you will get 0.67. You could try it on your own. The ratio remains the same. This problem up here is the factor label method. This is the process whereby we, did the wrong thing. Okay, this process right here is the factor label method. This is where the 0.625 moles of H2 times 2NH3 over 3H2. I use the mole ratio right here as my conversion factor. The H2 crosses out, the NH3 is what remains. We could try another one where we maybe do with the same equation, where we have something like 8 moles of N2 reacts with excess H2. How many moles of NH3 are produced? So look, when I see this, it's the same idea. And the thing that makes this a tiny bit harder is they throw in this distractor, excess H2. We can ignore that because it's an excess. Think back to the s'mores lab. You had left over of some of those ingredients. Well, here we have excess H2. We don't worry about it. We could do the same ratio, 8, or the same setup, 8 moles of N2 times, well, I go back to my equation again. This time I'm comparing N2 and NH3. Well, for every 2 NH3s, using the coefficients, I will use 1 N2. This will give me 16 moles of NH3. And so there we have it. We have 2 simple problems. We're using the mole ratio. Now things get a little bit more complicated when we start with a quantity other than moles. The problem I just did with you utilized this part right down here. But now what if I was given a quantity? Well, let's take our equation and put it back in here. Let's say now we started with 56 grams of N2. And I ask you, how many grams, so this is my question mark here, how many grams of NH3 can I make? Well, the idea is the same, but I need to first get the quantity that I'm given into moles. So now we go back to what we did, early in the chapter. Let's take our 56 grams of N2. Let's change it to moles. Well, for every 1 mole, there's 28 grams, and that will give us 2 moles of N2. I'm right here now, 2 moles of N2. Now I use my mole ratio. I want to get to NH3. We'll times that by 2 NH3 from the equation, 2, for every 1 N2, using the coefficients. That will give me 4 moles of NH3. So now I know I have 4 moles of NH3. Well, how many grams? Again, I use a mole conversion. When I use the mole conversion, I go ahead and I look at this and I have 4 moles of NH3 times 17 grams for every 1 mole. Well, 4 times 7 is 28, so that's 68 grams. If I do the math, that's my answer. This is a 3-step process. The first step over here, step 1, I use the mole conversion. I change the quantity. It could be in liters, it could be in molecules, but I change that quantity to moles. Then I take that moles and I use the balanced equation to find the moles of the next substance. Then I take the moles of that next substance and I convert it into whatever unit I need to. These are the easy and the medium stoichiometry problems. In class, we're going to practice these. The hard stoichiometry problems come in the next part, which are the limiting reagent problems. Now, when we did the s'mores lab, they were hinting at that. They were talking about limiting reagent because I gave you ingredients that weren't in the perfect ratio. Some of you had extra marshmallows, some of you had extra graham crackers. Depends on what you had. So anyway, we'll do that next time. For now, and in class, we're going to practice how to do the basic and the medium stoichiometry problems. Okay, thanks so much for watching. Have a great day.